Hello everyone, friends. Today, we have a traditional release of answers to the questions of sponsors, viewers and readers of the project. One of your favorite categories. I want to remind you that you can leave your question for the next video in the comments, providing it with the appropriate hashtag. So what? The surest way to ensure that your topic gets into the issue is to be our sponsor on any of the available platforms. Pavel Potsuluyev and Mikhail Ivanov were engaged in the answers for today's issue, and we voiced them. If you don't have any questions of your own, then I really ask you to write in the comments. What topic or what answer seemed to you the most interesting today? We are always happy to receive such feedback. Now let's get down to business. Hi there. If a stick with a length of 1 light-year is moved from one end to a conditional distance a kilometer, then the other end will react. That is, it will shift to the appropriate length in 1 year due to the speed of light limit. Where will 1 kilometer of stick go? The stick will be shorter for a whole year. First of all, it is worth noting that in physics there are no perfectly rigid objects that instantly transmit movement from one point to another. When you push one end of a stick of any length, even 1 meter, let alone 1 light-year, the shift is transmitted by a mechanical wave, in particular by elastic deformation, which propagates at a speed that is always less than the speed of light. If you imagine that you have shifted one end by 1 kilometer, then the other end of the stick will only know about it after the time it takes for a mechanical wave to travel the entire length of the stick. In the case of a stick with a length of 1 light-year, this means that the displacement will reach there after a time close to a year or more. After all, the rate of deformation propagation cannot exceed the speed of light and in fact will be much lower. In practice, the stick is slightly compressed or stretched in different areas for a short time, and then returns to approximately its original shape when the deformation wave propagates further. In other words, the extra kilometer does not disappear anywhere, and the stick does not become shorter for a whole year. The movement simply hasn't reached the far end yet. It is known from the special theory of relativity that no signal, including mechanical ones, can move faster than light in a vacuum. Therefore, a stick, no matter how long it is, cannot transmit a push simultaneously along its entire length. So the disappearance or circumcision of a kilometer does not occur. It's just that the other end waits for its push until the deformation wave reaches it. Good afternoon. I don't know if there has already been such a question, but is there any convention for the names of planets, galaxies, and other objects in the universe? If so, I would like to hear more about it. Yes, indeed, there is an official system of rules for naming various astronomical objects, and the International Astronomical Union is responsible for this. It has several working groups that have recommendation documents for assigning new names. If we talk about real examples, the planets of the solar system have historically been named after Roman and sometimes Greek gods and goddesses. It is obvious that there are either no new planets in our system, or there are a couple left somewhere beyond our reach. And if they are open, the rules will remain. Satellites of planets usually get names from mythology associated with the main deity of the planet. For example, the moons of Jupiter are named after mythological characters who were associated with the god Zeus or Jupiter. Dwarf planets like Pluto and asteroids receive the names proposed by the discoverers, but they must pass the approval of the masses. These are often mythological names, and sometimes the names of famous historical figures, scientists, and the like. When a new exoplanet is discovered, it is first given a technical designation. For example, HD 209 458b. However, the mass has a program called ExoWells, in which exoplanets and host stars can receive their own name, selected through public competitions. Such names are approved by the organization and become official. Most of the stars in the catalog have only catalog numbers, for example, H7001 or HD 170 to 167 for Vega. The ancient discoverer stars, Sirius, Betelgeuse, Vega, and others received historical names in ancient times. Many galaxies, nebulae, and star clusters have historically received their own traditional or popular names. For example, the Orion Nebula, Andromeda, and so on. However, for scientific purposes, catalog designations are most often used. ANGI C is 224 for the Andromeda Galaxy, ANGI C is 1976 for the Orion Nebula. The mass basically does not give fancy names to these objects, but they have been fixed historically or through popular culture. Greetings, thank you for your work. Since there is no detection of hypothetical dark matter particles, then can microblack holes really be the answer? Are microblack holes consistent with the observation of the Shar galaxy? Is there a chance to discover microblack holes, if they exist? I heard that there was a scientific article on this recently. Some researchers believe that a large number of microblack holes can make up part, or even all of dark matter. Primary collapses in the early universe. They are really capable of behaving like invisible gravitational objects interacting with the environment, mainly through attraction. This idea is also supported by the lack of convincing direct evidence of the presence of hypothetical dark matter particles, WIMPs and others, which researchers have been searching for decades in underground detectors to no avail. However, despite all the attractiveness, the hypothesis of microblack holes encounters strict limitations of observations. Two light black holes quickly evaporate due to Hawking radiation and do not live up to the modern era. More massive variants are tested by microlensing distant stars as well as indirect methods, X-ray and gamma-ray observations. As it turned out, their number or total mass is probably not enough to explain all of the dark matter. And yet they can make up a certain part of this dark component of the universe. Therefore, research continues, in particular thanks to new data from gravitational wave detectors. There are opinions and calculations that every black hole, if not every one, then correct me please, will disappear over time, because its body loses particles, mass during the evaporation process. But a black hole, this is a place where, in theory, a lot of particles should fall. So is the volume of evaporation greater than the volume of absorption? So much so that the black hole will eventually evaporate. Only exceptional particles that can overcome the speed of light can leave a black hole, but everyone falls into it. Because nothing moves faster than light. How does it even work? Or do I understand something wrong? Indeed, there is a hypothesis expressed by Stephen Hawking that black holes can evaporate. It has a spiral fall of matter beyond the event horizon of a black hole, due to which its mass increases. If we compare these two processes, the fall of matter is several orders of magnitude greater than the hypothetical evaporation. But the fact is that the amount of matter in the universe. Of course. So, according to one theory, someday all matter will fall beyond the horizon of black holes. And all black holes in galactic clusters will merge. And if dark energy continues to expand the universe, then galactic clusters will move away from each other, at a speed exceeding the speed of light. So when each such cluster becomes one big black hole, there will only be one process left: evaporation. If it exists at all, which is not yet clear. The basis of the evaporation of black holes. Quantum effects of vacuum in a strongly curved gravitational field on the event horizon. According to the formulas in the framework of this hypothesis, it turns out that the vacuum quantum state on the event horizon becomes unstable due to the curvature of spacetime and leads to the birth of pairs of quantum particles. One of them falls over the horizon of the black hole, and the other flies away from the horizon. Due to this, the black hole should lose mass, because the particle that fell over the horizon is borrowed from the vacuum, as it were. In general, it's somewhat embarrassing that this is now the best way to explain quantum gravity. A lot of things are simplified. Here is the case when simplifications confuse more than they help to understand. It remains only to wait for the appearance of brilliant popularizers who will be able to explain clearly, and without losing important things. Have astronauts ever had radiation sickness? How does NASA monitor the radiation dose received by an astronaut, and are there any protocols in case of exposure or threat of exposure? So far, no cases of radiation sickness have been recorded in people who fly into space. Astronauts on the islands have individual passive dosimeters. With their help, The accumulated radiation level for each astronaut is monitored during the expedition and after landing. The amount of radiation dose received is recorded. The device consists of 4 dosimeters that measure different types of radiation, and a screen that displays the measurement results. There is also a second device that performs the function of charging and reading data for transmission to Earth. These dosimeters are more accurate than commercial alternatives of the active type. Question: you said that there are successful projects that allow you to dock to active satellites and adjust their orbit. Can we develop a startup that would be launched into space and with the same mission, but in order to cling to Russian satellites? For example, reconnaissance, and bring them into the atmosphere. Such a project would be a gross violation of international norms, agreements, and laws. Any country that would have carried out such interference in the operation of another state's satellite would have been punished by the international community. All countries, both civilized and not so much, are afraid of such projects. So consider it a taboo at the level of the use of nuclear weapons. How does the space debris tracking system work in practice? How can you track objects that are only a couple of centimeters in size at an altitude of hundreds of kilometers? The space debris tracking system consists of ground-based radars and optical telescopes that record all objects in orbit around the clock, starting from a few centimeters in diameter. For example, the American Space Surveillance Network unites dozens of radar and optical stations in different parts of the globe. These radars send high-energy pulses and reflect signals from metal or other surfaces of space debris. Thanks to accurate measurements of the signal return time, as well as the beam propagation angle, the system determines the current location and speed of the object with great accuracy. To refine the orbit, telescopes are also used, which, by registering reflected sunlight, are able to automatically calculate trajectories. By the way, human intervention is required here only to check the anomalous values of observations. In addition to the United States, China and the European Union also have similar systems. If we talk about space launches, then during the flight, the launch vehicles or the satellite can be tracked in real time. And when additional elements are separated from them, all such fragments also fall into catalogs. If a chip falls into the atmosphere and burns up, it is excluded from the base. Updated data on the location of objects are transmitted to various satellite operators who can adjust the orbit of their vehicles to avoid collisions. Although full garbage tracking is still far from ideal, especially if the object is smaller than a few centimeters. Modern radars are physically capable of detecting debris with a diameter of about 2 to 3 centimeters in low Earth orbit. And every 5 to 10 years, the capabilities of humanity increase significantly. A lot of money is being invested in the development of computers for satellites. And wouldn't it be easier to use ordinary computers in some kind of protective capsule, for example, made of lead? Of course, adding a couple of spare devices for reliability. And in general, what is the difference between computers for use on Earth and in space? In fact, putting an ordinary office computer in a heavy lead capsule is not as profitable as it may seem. In space, mass is critical, so a thick layer of metal would be too heavy and would not guarantee perfect protection. In addition, high-energy particles hit lead and can form secondary radiation. And conventional processors and memory without special protection are quite vulnerable to radiation failures. And the cooling systems of terrestrial devices will not work in a vacuum. And any breakdowns in orbit are difficult and long to repair. Space computers have hardware protection against radiation, a well-thought-out fault tolerance system, and effective methods of heat removal. It's all literally embedded in their design. The materials from which they are made are carefully selected and tested in difficult conditions, from extreme temperatures to strong vibrations and a rarefied environment. Although their development is not cheap, but it saves a lot, increases reliability, and reduces the risk of critical failures. As a result, it is more profitable than sending bulky capsules with equipment that is not adapted to life outside the Earth into orbit. Suppose the Starship starts flying like a Falcon 9 right now. Let's also assume that due to this, the launch price has fallen a certain number of times. What commercial projects will become available thanks to this? Where will they start? First of all, they will start with the output of a new generation of Starlink. Even now, in the process of testing, they are trying to display models of these satellites. Since launches on the Starship should be cheaper than on the Falcon 9, almost all customers who ordered a flight on Falcon family rockets will be transferred to methane super heavies. But for this, of course, you will need to make a large door in the fairing of the Starship and not a narrow slit, as it is now. I think the most promising customers will be those who display large groupings of satellites. That will be somewhat different from communication satellites, since this niche is occupied. And in a few more Starship launches, you can build an orbital station with giant rotating modules that simulate gravity. And thanks to refueling in orbit, the first flights of prototype robots for mining on nearby asteroids may begin. A couple of years ago, I heard an interesting idea about the organization of a colony on the moon in lava caves. It was planned to use special robots to explore such caves. Is it known how this idea developed or what it turned into? Lava tunnels on the moon attract considerable interest as a potential place for a colony, because of protection from cosmic radiation and meteorites, as well as stable temperature compared to the open surface. Or to use robots for their research has been discussed since the beginning of 2010s, but in recent years, it has really acquired more specific features in a couple of projects. The Daedalus Exploration Project from the European Agency is a concept of a spherical robot capable of descending on a cable into holes light wells leading to a lava tunnel. The robot would have to move autonomously inside the caves, collect data, and scan the inner walls in 3D mode. And the concept is well from NASA. It was proposed to create a small lander with only a geological apparatus that would descend into lava tubes on the moon. The project was submitted as part of the NASA Discovery program, but has not yet been selected for implementation. There is still a chance. So far, no mission for direct exploration of lava caves has been officially approved at the level of the system we are launching. However, previous research and development give reason to believe that in the next decade, we may see the first demonstration works that will carry out reconnaissance of such caves. At the same time, NASA, ESA, and JAXA are leading or financing scientific and conceptual projects aimed at developing technologies for descending into deep mines. The main difficulty. This is the creation of a device that will survive in extreme conditions and at the same time be able to output data to the outside. We need repeaters, cables, autonomous navigation. Protection from radiation and micrometeorites really makes lava tubes attractive for building bases. Numerous projects of lunar settlements, including those from NASA and NASA, provide for the arrangement either under the surface or in ready-made natural voids. But for now, all this remains at the level of scenarios and architectural concepts. Officially, the Crew Dragon is not designed to correct the IS orbit, and theoretically, the Crew Dragon can make a correction instead of the Russian ships. If not, what modifications need to be made to make this a reality? The Crew Dragon is designed for people, but its modification Cargo Dragon demonstrated the possibility of changing the orbit of the IS. On November 8, 2024. His Drac engines are weak, so by turning them on for 12.5 minutes, it turned out to increase the orbit of the station by 1/10 of a kilometer at apogee and 1 kilometer at perigee. So in theory, you can add fuel tanks to it and adjust the orbit. The Singa's ship can also change the orbit of the station. He is more effective in this regard. As always, many thanks for your work. What difficulties can arise when creating artificial gravity by rotation? How feasible is this, and is there any interest in it? With the current level of technology, this method seems plausible. The idea of artificial gravity by rotation, for example, in the form of a rotating module of the space station, is really able to reduce the harmful effects of microgravity on the body. However, several key difficulties arise in practical implementation. Firstly, in order to provide a comfortable level of pseudogravity, the station or module must be rotated at a certain speed. It must have a sufficient radius. If the radius is small, the rotation speed increases, which causes undesirable effects. For example, the forces of Coriolis can cause liquids and objects to move in an unusual way. And people have problems with the vestibular apparatus and a feeling of dizziness. Secondly, from an engineering point of view, the creation of a large rotating compartment requires complex docking mechanisms and systems capable of withstanding constant rotation. In addition, special transition nodes or methods of transmitting electricity and data between rotating and non-rotating parts of the space station are needed. Plus, the rotation is guaranteed to add vibrations. And the vibrations. This is something that they always try to avoid in space. They affect the equipment and literally loosen the nodes and fasteners of the stations. And thirdly, in real space projects, especially in low Earth orbit, other methods of dealing with the consequences of weightlessness are more often used so far. Daily physical exercises, special suits to support muscles and bones, and also take banal vitamins and minerals. A full-fledged rotating module is considered a complex and expensive solution. Nevertheless, the scientific community remains interested in the study of artificial gravity, especially in the context of long-range manned missions, for example to Mars, where prolonged microgravity can pose a serious health hazard. We all walk under God. If something happens to Musk, who will inherit his empire? How important is it, who exactly, or everything will continue to develop at the same pace and in the same directions without Ellen? I can only answer within the framework of Musk's space enterprises. SpaceX, a private company, but it also has its own organizational structure with deputies and leading engineers, led by the president and chief operating officer of Gwynne Shotwell. She has repeatedly demonstrated the ability to manage key projects. For example, it was under her leadership that most of the operational processes for launching Falcon 9 rockets and developing Starlink were carried out. Musk's departure, of course, would greatly affect Space 10 in terms of strategic vision and media. But the basic projects would continue to develop at the expense of already formed teams and a roadmap developed for many years to come. The company has a large base of regular customers, has a business that allows it to invest income in innovation, and it has a huge staff of talented engineers who are able to implement these innovations. In general, both SpaceX and Starlink, as part of it, have an established infrastructure, a staff of highly qualified engineers and managers, as well as formal management mechanisms. Of course, a lot depends on Musk's personal charisma and ideological leadership, but SpaceX has managed to build internal processes over the years so that in case of force majeure, it can continue working based on existing plans and funding. This is far from a leadership startup, but a real self-sufficient corporation. Is there a difference in providing first aid in space and on Earth? First of all, there is no gravity in space, so microgravity complicates the provision of medical care. For example, when we stop bleeding on Earth, we focus on how the blood flows down under the influence of gravity, and apply bandages in a certain way. In space, liquids behave completely differently. Blood is distributed more evenly through the tissues and does not accumulate at the bottom. In addition, any manipulations with the patient require additional fasteners, because both doctors and victims can easily come off the surface. The second important point: extremely limited resources. There is only a basic set of medical equipment on a space station or spacecraft: syringes, standard medications, instruments for emergency procedures. For more complex injuries or illnesses, the crew has to rely on instructions from ground medics, transmitted over the communication channel. Critical situations usually involve an urgent return to Earth, if possible, since a full-fledged operational is absolutely necessary in space. Well, not to create. That's why NASA and other space agencies regularly update emergency protocols and train astronauts in case of emergencies. Therefore, if we are talking about potential serious injuries, we are talking more about pre-medical care, about maximum stabilization of the patient. For the time being, there is simply no one and nothing to carry out further treatment in space. However, If we talk about the relatively distant future, then a self-sufficient large base on the Moon, for example, may have specialists and materials or equipment necessary for even complex operations. Although here, the Earth will remain a much better option for a very long time. Thanks for the work and the question. The Sun has satellites. These are planets. Planets have moons. These are the satellites themselves. And if the satellites have satellites, artificial ones don't count. If not, why not? In fact, the satellites of satellites in English, they are sometimes called submoons or submoons in the solar system, have not yet been discovered. The main reason: gravitational conditions. A satellite orbiting a planet, simultaneously experiencing the gravity of the planetary host and the Sun itself. In order for it to have its own natural moon and stably exist, a very specific range of distances and orbital parameters is needed. In most cases, the planetary gravity turns out to be too strong, and any small object either breaks out of orbit or falls on the surface of the satellite. Therefore, a stable solar satellite is not preserved in real conditions for millions of years. At the same time, asteroids with satellites are found in the solar system. The most famous example. This is a Didymos with a small dimorph satellite. It was there that the DART umbrella flew in at 2022. There are also binary asteroids and dwarf planets with small moons, for example, Pluto-Charon. However, these are more binary systems than a satellite with its own satellite. So far, only planetary moons have been discovered without confirmed grandchildren. Nature does not allow them to exist for a long time in stable orbits. Question: a cluster carrier of universal acceleration modules. Why don't they make them? Since the days of the first inflatable atlases, it is much easier and quite possible to make a constructive one. Their hull tank weighed 2.5%. Work with the geometry of the airframes of the blocks that form a protective shell at the lifting stage. The tanks are suspended and significantly lightweight. At the return stage, the airframe of each block. This is a heat shield and a wing. If necessary, controlled rocket dynamic braking on a trampoline on the remains of fuel. The idea of a cluster launch vehicle with inflatable tanks and reusable airframes sounds attractive from the point of view of saving weight and versatility, but in practice it turns out to be too complicated. For example, the balloon-like design of the tank really allows you to reduce the dry mass to 2 or 3%, as it was in the early atlases. However, this architecture requires constant internal pressure in the tanks, and this makes it difficult to dock between individual blocks, check the integrity, and general installation in this cluster. In addition, if each unit has its own wing, a heat shield, and engines for controlled braking, this significantly increases the number of mobile and vulnerable components. The next problem: ensure aerodynamic stability during takeoff. Usually, when several identical blocks are connected around the central core, this is done in the form of parallel accelerators, like in the Delta IV or Falcon Heavy rockets, and not a solid shell. If you try to create a protective fuselage for many gliders, you will also have to synchronize the fuel flows, the structure of the bearing surfaces, and ensure that there are no mutual fluctuations at high speeds. And in addition to aerodynamics, there is a question of thermal protection for each unit. The heat shielding layer, which will withstand supersonic entry into the atmosphere, must be strong enough. This again increases the mass and complexity of the project. Finally, the return of the planners will require an additional landing system, or, as you mentioned, a trampoline, with an inflatable shock-absorbing coating. This is another technical task that will require the transportation of additional fuel for braking, or complex parachute aviation systems. Today, most companies seeking to reuse the stages choose a vertical landing with jet braking, like SpaceX or Blue Origin. Or they plan to capture elements of the rocket in some other way. All these methods so far seem less complicated than creating a universal glider shell with light inflatable tanks. Question: I would like to learn more about orbital stations. Good afternoon. Fortunately, while we were preparing this issue, a video about such stations and 2 specific projects was released on the channel. And on our Ukrainian language channel, there is a whole podcast issue where I additionally revealed this topic. The links will be in the description. Thank you for your hard work. It would be interesting to learn about the hardware and software elements of modern spacecraft. What are the current requirements for electronics? To what extent do these electronics chips, processors, controllers differ from publicly available ones? And what software technologies are used in the development of software for them? Modern spacecraft have very strict requirements for the reliability and stability of electronic systems in the face of extreme factors of the space environment. Radiation, protons, ions, and high energy, strong temperature changes, vibrations, and vacuum. Therefore, even if equipment compatible with mass chips or processors is used somewhere, it, firstly, undergoes additional qualification and testing, and secondly, it is often supplemented with special radiation-resistant components. As we have already discussed today, this affects the price and development time. Space chips and controllers are more expensive, their availability is limited, and the verification cycle is much longer than that of conventional commercial equipment. Special production methods reduce the likelihood of failures and other damage caused by charged cosmic particles. RAM in space usually has mechanisms for detecting and correcting errors at the bit level to avoid errors that can stop computers from working. Plus, there may be duplicates of key blocks in microprocessors and target controllers for critical tasks. Cores, power supplies, the same memory, which allows you to verify the results or switch to a backup module in case of a failure. If we talk about specific processors, NASA, for example, uses the RAD 750 architecture. And such chips have a lower clock frequency compared to modern desktop and even mobile processors, but they are much more reliable. Europe has its own architecture, which is called Leon. Manufacturers of small devices are now actively experimenting with technologies because they are reliable and require very little power. If we talk about the program code, they usually use a Unix-like operating system. The software itself is written in C, C++, as well as Ada. Due to strict typing and historical popularity in the aerospace industry. Well, for data analysis and ground testing, Python is usually used, but not on the end devices themselves. Very interesting questions and answers, thank you. My question is, when will people be able to fly to Mars? Is it realistic in, say, 10 years? Oh, this question is almost the most frequent in our reference and live broadcasts. Well, my answer is unchanged. Add about 10 years to the date of return to the Moon. So much for the most optimistic year of a manned mission to Mars. In the last issue of the reference, there was a question about the burial orbit, and your answer prompted an additional question on the same topic. If it takes fuel to go into a burial orbit, why is it that instead of reducing the speed of the satellite and burning it in the atmosphere, it is accelerated even more and left to loiter in space for thousands of years? First of all, it all depends on the altitude of the orbit. In low Earth orbit, satellites are indeed most often lowered into the atmosphere so that they burn up upon entry. This requires a relatively minor speed adjustment because they are already located near dense layers of the atmosphere. But geostationary satellites hang at an altitude of more than 35,000 kilometers above the Earth, and much more fuel is needed to reduce their speed to a level sufficient to enter the atmosphere. Therefore, operators prefer to slightly raise the orbit by 200 or 300 kilometers and send such devices there to the burial orbit. The second explanation, which is also related to fuel, is resource optimization. The fuel reserve on board the satellite is usually calculated for regular correction of the orbit in order to keep the device in a given position, and there is a small remainder for the final maneuver to raise the orbit several hundred kilometers higher. This is a smaller delta V, that is, a change in velocity, than in the case of a decrease in it up to a collision with the atmosphere. Thus, burial in space turns out to be more economical than complete disposal on Earth. And this is officially enshrined in the standards for reducing the volume of space debris. And besides, it's worse to lower the orbit of a geostationary satellite a little than to raise it a little. After all, then the new geostationary vehicles on the way to the working orbit will have to make their way through the ring of idle satellites. Question: where and when in Europe can you watch a rocket launch? In Europe, in the near future, it will be possible to do this at spaceports in Sweden and Norway, as well as in the UK. You can see their list on the screen now. But to be honest, they will only be put into operation. Therefore, it is unlikely that civilian viewers who do not work for launch operators will be allowed there. Question: if R and other systems were formed after the explosion of protostars, which formed all the heavy elements, then where are the remnants of these stars? The remnants of protostars that have worked their way out and thrown heavy elements into space have not really disappeared anywhere. They are found in the form of supernova remnants, such as the Slave Nebula, or in the form of gas dust nebulae and more compact objects such as neutron stars and black holes. When a massive star explodes with a supernova, it throws out into interstellar space most of its matter enriched with heavy elements that have been synthesized in its bowels during its lifetime. Then these stellar remnants, gas and dust, can become the building material for the next generation of stars and planets. Our star system, like many others, was formed from mixtures of hydrogen, helium, and these heaviest elements, scattered by interstellar space after the explosions of ancient stars. Over billions of years, supermassive stars have flared up and scattered, creating nebulae, and young stars were formed from their matter. Thus, we are all descendants of several generations of stellar collapses and supernovae that occurred in our galaxy. Question: scientists are dealing with the issue of providing oxygen to people on Mars. But, as you know, a person uses not pure oxygen for breathing, but a mixture with nitrogen, which is 78%. Divers use helium instead of nitrogen. Where to get nitrogen, or at least helium, on Mars? Great question. In fact, the problem of supplying the breathing mixture comes down not only to the production of oxygen, but also to the presence of ballast gas. Nitrogen-oxygen mixture is most often used in space missions because pure oxygen under high pressure is very flammable. Because of this, a well-known tragedy occurred with Apollo 1. The International Space Station, for example, supports 21% oxygen and 79% nitrogen. In the early Apollo flights, mostly pure oxygen was used in the cockpit, but under reduced pressure, which reduced the risks of fires and the mass of the ship. But for long-term missions to Mars or bases on its surface, it is still really more convenient to have a mixture of gas in close to the Earth's proportion. Where to get nitrogen or helium on Mars? The atmosphere of the red planet contains about 1.9 or 2.6% nitrogen. Therefore, certain technologies could separate it from the atmosphere. Also, the Martian soil may contain a compound with nitrogen, for example, nitrates. As for helium, there is very little of it in the Martian atmosphere. Therefore, for now, it is easier to consider transportation from Earth or search for alternatives. For example, the use of an oxygen-nitrogen mixture. Divers on Earth really often use gel mixtures because helium is lighter and does not cause nitrogen anesthesia under high pressure. But in the Martian conditions of ultra-low atmospheric pressure, this is a less pressing issue. Currently, most Mars exploration projects involve integrated life support systems operating on a combination of imported supplies and local oxygen production. For example, as in the MOXIE experimental module on the Perseverance rover. But full-scale production of nitrogen or helium still requires detailed research and technical solutions. Does the density of matter of the space through which photons with different wavelengths pass affect their speed? Indeed, if there is scattered gas or plasma on the way from the light source to the observer, the light will slow down. Curved space will also increase the signal transit time. Let's analyze this with the example of several interesting cases. In the 2018 year, scientists Jean-Pierre Macquer and Zhongyi Kuai of the Curtin Australian Institute of Radio Astronomy analyzed radio signals from fast radio bursts. This is a relatively new phenomenon in astronomy, when very powerful radio sources appear for a very short time. The mystery of their origin is being studied now, but in this study, scientists were interested in how the components of fast radio bursts disperse and arrive differently in time. The intergalactic medium is not empty, it contains a rarefied and very turbulent plasma. It was found that the components of a radio signal with a longer wavelength scatter more strongly and come later than with a short one. The scientists were also able to establish that the scattering and deceleration does not occur in the galaxy of the source of the fast radio burst, but in the intergalactic environment. To do this, they built two models. In one, the scattering occurred in the source galaxy, and in the other, in an intergalactic environment, scattering indices at various redshifts were compared. In other words, simplifying it, we can say how far away the galaxy is from us. After all, the further away, the stronger the effect of space expansion, and the more distant the galaxy is from us, which is what causes the red shift. If the main scattering occurred in the source galaxy, the scattering would be much weaker, depending on the increase in redshift. Comparing the simulation results with observations, they showed that the main effect is caused by turbulent plasma in the intergalactic medium. Thus, scientists have obtained a tool for estimating the amount of turbulent plasma in various parts of the intergalactic medium. A similar delay of individual light components, as well as scattering, was detected by overobservation of signals from pulsars. We compared data from pulsars inside our galaxy and those in other galaxies. The story about the delay of photon radiation in comparison with gravitational waves during the merger of two neutron stars. When answering your question, it will not be possible to consider only one such phenomenon, called a kilonova, was observed in the year 2017. And a significant delay in X-ray radiation was apparently observed due to the fact that the initial jet of high-energy particles was not directed at the Earth. Presumably, the jet should arise precisely at the moment of the merger of neutron stars together with gravitational waves. And the X-ray that was later recorded by the Chandra telescope, as well as radiation in the visible and infrared ranges, was a re-emission of the medium surrounding the merged neutron stars. And this color came a few hours later than the gravitational wave signal, because it took time for a jet of high-energy particles to fly and hit this medium. Powerful gravity bends the fabric of spacetime. The uneven gravity of galaxies bends spacetime inhomogeneously, so light from a distant source can travel in different ways for different times. One example is a double image of a quasar located 8.7 billion light-years away from us. The light from it passed through an elliptical galaxy located at a distance of 3 as many as 7/10 of a billion light-years. Also, the gravitational influence was exerted by the galactic cluster, which includes this galaxy, between us and the quasar. So, the time difference between the two images of the quasar is 417 days. As you can see, both the intergalactic medium slows down light, and the powerful gravity of compact objects bending space increases the path traversed by light, which makes it travel longer from the source to the observer. Why does light, having no mass, deviate near stars or massive bodies? Let's clarify this so that there is no misunderstanding of the previous question. Light really does not have a rest mass, so gravity does not affect it directly, as it does bodies with rest mass. Gravity bends the fabric of spacetime. The more mass is concentrated in a particular volume, the stronger the curvature. Space is three-dimensional. It is quite difficult to imagine how it can bend if you are not familiar with such a concept yet. Therefore, for analogy, let's take the two-dimensional space of a rubber sheet on which a ball rolls. While the sheet is flat, our ball rolls in a straight line. If a heavy ball is placed in the center of the rubber sheet, then the small ball will no longer roll straight, but in a spiral, although it has no mechanical connection with the heavy ball. So is the light. In the case of a curved gravity of space, the shortest path for light is not a straight line, but a curve. It is also commonly called a geodesic line. This is the shortest path between 2 points in a curved space. For example, let's take a map and try to draw a straight line between two remote cities, and then compare its length with the length of the path of an airplane flying between the same points. The pilot plots a flight taking into account the shape of our planet, because he cannot fly through the Earth. Therefore, the geodesic line for the aircraft turns out to be curved and the shortest in comparison with the straight line drawn on the map. In the same way, light in a space curved by gravity flies along a geodesic line, which is a curve, not a straight line. Why not put fuel tanks into orbit? So that the ships that spent their tanks on launching into orbit would have this resource for further travel. A really good idea for flights beyond low Earth orbit. It could have been started 10 or 15 years ago, using rockets that were already flying at that time. But the orbital fuel storage facilities would jeopardize the SLS rocket project, and Alabama Senator Richard Shelby forbade us to even talk about it in the public field. And it is in Alabama that the SLS Development Center and most of the jobs related to the project are located. SLS has flown only once so far, and the cost of the project has repeatedly increased. SpaceX's Starship project, still under development, has shown that it is possible to create a rocket system that includes infrastructure for refueling in orbit and much cheaper than SLS. By some coincidence, Richard Shelby resigned. And now Blue Origin is also developing the Bluewing platform, one of the functions of which is the orbital storage of cryogenic fuel, which is necessary to fulfill the obligations under the Human Landing System contract. So now, two big players in the industry are working on orbital fuel storage. There are also startups that have announced similar storage facilities for small satellites, but they are still far from practical implementation. In addition to the quite obvious advantages and orbital fuel storage facilities, there are, let's say, not minuses, but difficulties. It is necessary to ensure a stable flow of launches for their timely replenishment. The Starship has not yet achieved reusability and a high frequency of launches, and Blue Origin has not yet managed to make even a partially reusable rocket. But both companies are not desperate, and they have everything in order with financing. As dying stars, in which the thermonuclear reaction has ended and consisting of heavy elements unsuitable for further fission, with a positive energy yield, as a result of the explosion, can serve as a building material for new stars. After all, what remains of them is unsuitable for thermonuclear reactions with a positive energy yield. Good question. Let's explain everything now. The fact is that any star consists of a core and outer layers. Thermonuclear reactions occur only in the core. Since we are only talking about stars exploding at the end of their lives, we are automatically only talking about very massive stars that are tens of times heavier than the Sun. In such stars, the core at the end of existence consists of iron and nickel, and the mass of the core is 1 to 2% of the entire star. When thermonuclear processes stop going on in the core, that is, there is no more energy to balance the gravity of the outer layers, the collapse begins. Protons merge, and neutrons are formed. The mass of a neutron is greater than the total mass of an electron and a proton. So the formation of neutrons goes with the absorption of energy. Neutrinos are also released, which carry away energy from the nucleus. Both of these processes accelerate decay. Before the collapse, the radius of the star's core is approximately equal to the radius of the Earth. After the collapse, it is about 50 kilometers, and the collapse itself takes a quarter of a second. After that, the core size change stops abruptly, the outer layers fall on it, and the core size increases slightly, it balances. Due to this balancing of the core, a supersonic shock wave occurs in the incident gas of the outer layers. And after 30 milliseconds, the amount of matter carried away by the shock wave is equal to the amount of matter in the shock wave itself. It turns out something similar to a traffic jam between the falling gas and the shock wave being carried away, so that the shock wave dissipates. And the neutrinos continue to fly out of the core and are captured by the dense gas of the outer layers, so that these gases are heated up. And just crazy convection begins there. After 300 milliseconds, due to this convection, the shock wave forms again and penetrates through the entire star. Because of it, the process of explosive nuclear fusion begins, during which heavier elements appear. The shock wave dramatically heats and accelerates the stellar envelope, so that in a few hours it reaches the surface, and, tearing off matter from it, moves at a speed of 1/10 of the speed of light. To an outside observer, it looks like a star exploding. Its brightness increases dramatically to a magnitude of 10 billion suns. The average velocity of the outer layers being dumped is 3/100 of the speed of light. And by mass, it's about 98% of the original star. The decay of the remains of the star is slower than it could be, due to the additional energy of gamma rays released during the decay of radioactive elements, primarily nickel and cobalt, formed in the last wave of explosive nuclear fusion before the breakthrough. Yes, elements heavier than iron were formed at the same time, but there are not many of them by mass. Then, the discarded remnants of the star scatter so far that they mix with interstellar gas, consisting mainly of hydrogen and helium. Then new stars are formed from a part of what has been mixed, in which the content of elements heavier than hydrogen and gel is already higher than in the stars of the previous generation. I'm sorry for taking so long to answer your question, but the process of a supernova explosion is very exciting. Well, these were all the questions that the sponsors asked us and that we selected under the previous issue. You can leave your impressions in the comments. For example, write which answer you like the most. We read all comments and will try to take into account your wishes. Let me remind you once again that you can ask a question directly in the comments by equipping it with the hashtag question. And if you are a sponsor or patron, then in a special post in the community tab on YouTube or on the Patreon itself. Links to such posts should be in the description under this video. That's it for us. We'll meet in the next issue. In the meantime, you can watch a playlist with previous releases of Cosmos reference on our channel. And by the way, I just can't help but remind you that the column comes out solely due to the fact that we have sponsors on YouTube and Patreon. These wonderful people donate from $1 a month, and in return, in addition to the opportunity to ask a priority question, they get early access to most of the videos on the channel, to long reads on our website, thanks at the end of each original video, and a pinch of exclusives. It is sponsors who allow us to do what we love without looking back at advertisers. The thealphacentauri project is fully maintained by the community, and we are incredibly grateful and happy that such cool people have gathered around us. If you can and want to join them, you can do it by following the links in the pinned comment. In addition to a monthly subscription, it is possible to send a one-time payment. Thank you.